Well, thank you very much, Ian, and it really is a pleasure to take part in the second day of the George Nemetschek Institute's opening event. Certainly, it's an institute that we're very happy has come to fruition since the ideas of using AI in the built environment in general, and BIM in particular, are very close to all of our hearts and minds. And so I thank very much for the opportunity both to present now, but more in general, for the investment in this branch of research. And so I'm going to share this set of slides. I've chosen to talk briefly about BIM and AI and to try to touch on some of the more fundamental research challenges as we see it. I will focus very much on the aspects of building information modeling. Of course, this is too broad a topic to cover everything. And so I will try to, at the end, focus your attention on the question of, as I've written it down here, a statement that goes like this: we progressed from paper to CAD somewhere around the 70s and 80s as an industry, broadly speaking. And roughly centered around the year 2000, we have begun a shift, and we're perhaps still within that shift, to broad use of building information modeling. But then, of course, the question arises, what comes next? And what's the role of AI in that future development? So that's where I'm headed. Artificial intelligence, of course, is very broad. And I guess you don't need me to lay out the different aspects of it. It's used for a various range of things, and there are many tests of how intelligent or semi-intelligent some kind of system may be. But broadly speaking, we can talk about symbolic AI, such as knowledge-based expert systems, heuristics, using heuristics and rule inferencing. And we can talk about sub-symbolic AI and about statistical learning, where the actual notion of the concepts themselves is less important than the patterns of the numbers or statistics that represent that information. And for my purposes now, in the context of building information modeling, for the purposes I'm interested in, I want to focus just on these 5 of those aspects, and specifically on reasoning, on knowledge representation, on planning, on learning, and on natural language processing. And so in these areas, there are really 3 kinds of broad areas of tools that we use. There are the inference engines, which have been around for some time, mostly the expert systems, and some case-based reasoning, perhaps these days less common than it once was, within grounds of research. And then the whole population of evolutionary and biomimetic algorithms, which we generally consider to be useful for optimizations, for goal seeking, for testing utility functions, and so on. And then the much more new and perhaps more broadly recognized area now of machine learning, where we're doing classification, clustering, and other tasks, and which, of course, may be supervised or unsupervised. And particularly, I think most of us are keenly aware of the challenges of finding major labeled data sets for the case of the supervised learning situations. There are many applications of AI with building information modeling, and I've tried to list a range of them. Some of them, the first 4, relate to design phase primarily, not only, but primarily. The next 2 or 3 relate to the construction phase itself, starting with monitoring project status data and production planning, control, simulation, optimization, and of course, the fabrication and construction itself using a range of robotic methods and others. Supply chain integration, I've listed 2, and finally, there is a whole range of AI applications in the areas of smart building operations and maintenance. And most of what I will speak about now concerns the section from generative design through to production planning and control. So if I, for a moment, try to step back into the past and then step over the stepping stones of the present and then look into the future, we might consider what the origins of AI are in the built environment. And largely they have to do with expert systems, with knowledge representation, and with various aspects of learning. So I list two, I've cited two at the bottom, one very well known at the start of applications of AI, High-Rise, a system built by Mary Lou Maher and very much influenced by her supervisor, Jean Giraud at the time. And that had to do with compiling an expert system to do structural engineering layout for high-rise buildings, for towers. A much less well-known one was called Expert Interactive Design of Concrete Columns. And that was something that I worked on in the mid-80s at MIT with Oral Bucas-Turk. And both of those, what's common to them and many other systems at the time, were very early, as you realize. They were all expert systems. They all used symbolic representation of the buildings, but there was absolutely no possibility of interoperability or of cross-use because every system had its own representation mode or method, and never the twain shall meet. Now, that's interesting because research in the 80s and 90s was very much restricted to symbolic AI, ruling inferencing. But it was a time when we did not have symbolic representations in building designs, or at least certainly not in the mainstream. Most of mainstream structural engineering architecture were using CAD for production, specifically AutoCAD, and more sophisticated systems like Sonata and Reflex were not yet very common or very well known. So it's really not until the advent of what we now call building information modeling around 2000, it's become more widespread, that we actually do have symbolic representations of buildings. And yet, I think all of us feel the frustration still that we're not really there yet, because even those BIM representations are very far from perfect. We have very broad variations in modeling practice. Something that was well understood then, but has become absolutely well understood now, is that software applications are very domain specific or task specific even. And so they have very specific ways of relating to the data, and the data models follow suit. And so again, the problems of interoperability very much remain with us. And so there's a great deal of redundancy in model exchange schema so that they can meet the needs of many, many domains. And yet it's exactly that broad application that prevents very common and easy exchange, because there are so many alternative ways to represent the information. And so we arrive at 2021, and we find that there are quite a wide range of AI applications in industry and in research. There are engineering companies that are applying AI for optimization in design, certainly for generative design. Many companies are offering services now, and also, interestingly, machine learning-based applications of case-based reasoning to replicate design from the past. And the others that I have listed here. And one particular area I'd like to pick up on, because out of personal experience, it's something we've worked in quite a bit, is the area of automated code compliance checking. And here in this area, we see that one of our biggest challenges is that even most of the existing software applications that exist now for industrial use require one to take on a step in the process called normalization. And that normalization step, which sits here in the middle, requires you to adapt or update the standing representations of the BIM model, whether that be an IFC or anything else, to the representation that is understood by the rule-based code checking engine. And that step of normalization can often be quite laborious, but more than laborious, it can also be soul-destroying, in the sense that you have to replicate it many times every time that you want to repeat a check when the design changes for one reason or another. And that really is a very big retarding factor on the way that these systems are used and on the way that they are built. To speak of another application that's very common, or is becoming very common, is this idea of using computer vision to acquire information directly from site during construction to allow one to compare things one across the other. And you see here an image from a screen view from OpenSpace AI. Now, there are other companies that do this too, and I know that we will hear later today from Manny Gopal, I'm sure similar and more advanced things. Companies like BuildDots, for example, do a very similar thing, but include identification of objects in the scene from the video feed, and then cross-checking of those objects to the objects in the BIM model, including comparisons of presence or absence, but also location, precision, quality checks, and other things. And there are, I think, we will see more and more of these systems in production use in industry. But for both of these things, and for many applications, we see that one of the areas that we really need to improve is this area of the representation, the computer understanding of the models. And an approach that we are working quite a lot on to develop that is called semantic enrichment, where the basic idea is to apply AI tools to interpret and enrich the semantic content of models so they can be reused for multiple purposes. And in particular, what we're trying to do is to say the receiver should be able to understand the model they are receiving. If the model they're receiving does not contain enough semantic information defining either objects or relationships or both, then the receiving application should be able to supplement those on its own. And the fundamental thinking behind that is to say, much as a person might receive a drawing or a BIM model, any human being vaguely trained in construction, engineering, and architecture will be able to understand the meaning of the images and of the content, even if they receive a computer file. They'll be able to understand more content than any computer system will be able to independently. And in that sense, they're actually enriching visually what they're seeing visually, using their mind to interpret and identify concepts and objects. So semantic enrichment says, let's see if we can train computer systems to do that. And the image on the bottom left here of an apartment is an example of that. Most of us could look at this and say, oh, I know what that is. That's an apartment. And here is the front door. And this is obviously the kitchen and the living room. And so these must be balconies. And here must be bedrooms in that case. And so here's a bathroom. And probably this room is the master bedroom because it's connected to a secondary or an ensuite bathroom. Now, those kinds of interpretations are exactly what we're talking about in semantic enrichment. So to try to automate this, we've tried a number of different strategies. And I want to show you a comparison quickly between the first way in which this was achieved using machine learning, using a classifier trained using a decision tree algorithm, based on a fairly small sample of some 60, 70 apartment models. And interestingly, it was able to classify all of those rooms correctly, but only if you were to do the algorithm we applied required recursive application. That is to say, you train a classifier, you run it, you identify the first room. The first room type being that which achieves the highest level of confidence, because most of the other rooms have fairly low levels of confidence. Once you have one room, you have additional information, because now you're able to say that the rooms adjacent or with access to that room are adjacent to access to, for example, the living room, which is an additional feature that we now know about those rooms. You then retrain the model with the new feature, run it again, and identify the next highest confidence room. On each recursive step, you can set a threshold for percentage confidence and accept those and then continue to do the others. And it turns out that by doing that within 7 or 8 steps, you can pretty much identify all the rooms in an apartment based on fairly small samples. Now, our learning from that as researchers, amongst other things, was that the relationships between rooms are very significant in identifying their function. And that's obvious to us all, that rooms are adjacent to other rooms because they fulfill certain functions. And so we then posed the question, what happens if we provide a graph representation rather than a tabular representation of the objects? And in this graph representation, we can then, as you see here, provide these additional edge features of doors or walls or windows or access and so on, even virtual walls, which exist here, for example, between the living room and the dining room. And then that may allow us to use graph neural networks. So we tried that, and I do want to recognize my PhD students in Jian here at the Technion who's been working on this. And interestingly, we then tried a single run of a number of different tools, decision tree, machine learning, supervised learning algorithm, support vector machine. And as you can see, the average accuracy here, 55%, here, 58%. Some rooms are easy to identify, but others, as you see here, for example, the laundry, are easily confused with other rooms like the balcony or the toilet. And using the support vector machine, again, it was very easy to identify the dining room and some of the other rooms, but almost every other one had confusion. And indeed, in this case, the laundry room was never identified correctly. Again, using a single run. We know that using the decision tree recursively, we could reach close to 100% on them all. But then we tried a graph neural network called GraphSage, which is generally used for identifying clusters of nodes within much broader networks. And here in this case, you can see that the clustering among different rooms is quite good. And so off the bat, in single run, we're already able to achieve 73% with close with 100% again on the living room and very high values for most of the others. Now, that's not to say that we want to recommend using only GNNs, but what we're learning from this is that a proper representation of the relationships among the objects using a graph is a good opportunity to move to using GNNs, which then allow us to do much better work. And so we've used semantic enrichment in a variety of areas, like reality capture in the CBIM project with other partners, and then with newer research challenges, modeling existing buildings or infrastructure. Here again, we see the bridges done in partnership with our host here at TUM with Andre and his then students, Simon Dahm and others, and together with Yanis Proulakis and others at Cambridge. In doing this, we were able to take geometric models and identify all the objects in those models, in this case, using rule inferencing. We have also used the same approach on fairly complex code requirements. This, for example, for identifying and checking against design a security room. And just an example of a complex clause, at least 70% of the cumulative length of the walls of a security room must be directly supported continuously through to the foundations, meaning they must have continuous walls running down. And that's the kind of thing that's really quite complex to check. And this was actually solved in the end by preferring a semantic enrichment process where it could go through, identify these walls, identify each wall's percentage of contiguity with the walls below it, do that in a chain fashion recursively, and eventually simply enrich each and every wall to say how many % of that wall were contiguous down to foundation, which then makes the final check, do you have 70%, a fairly straightforward greater or lesser than question. So where are we? And let me try now, as I wrap up, I guess, to try to tackle this question of paper, CAD, BIM, and what next? Because I want to argue that what we learned in applying AI in the area of code checking and other things was that the representations of the objects in the model are critical to the way that we apply AI. And in that sense, using graphs is a very good solution. So we've had paper. We see here images from the Middle Ages. We've had CAD, and we all understand that fairly well. And now we have BIM, which many people do understand well and is very well embedded in practice. But we still have problems. And those problems are mostly related to what there is in a BIM model. And what there is in a BIM model generally is geometry, some other information about the objects in the model, and some relationships and semantics about those objects. But there is a lot remaining here that is missing from BIM models. And it's that kind of information, implicit geometry, that we know as professionals exists there but has not been modeled. And other information that we can assume or interpret should be there. And many semantics that we can recognize, such as structural relationships between objects, which should be modeled. And that's different, of course, for different purposes. Were I to do structural analysis or mechanical or energy analysis, I would need different things. So a lot of this information is there, but it's inaccessible. And that's really the reason for semantic enrichment. And the reason I come back to this is this, that to reach real kinds of interoperability, what we really need are artificially intelligent, collaborative, concurrent, federated, property graph cloud modeling BIM systems. And what do I mean by that? I'll show you this very briefly. I know that Ian is already present, so that's my clue that my time is almost up. But I will take 2 minutes, if I may, to wrap up and say this. We're working now in a European project called CBIM, where we have many very talented students and professors. And what we want to say is this. One of the ideas that's coming out at present is this. Let's assume we have an architectural model and we see a column of 3 floors. And that can be represented in a graph using both an ontology at the top of the schema and the instance below. And if we load that up into a property graph database like Neo4j, we can represent it in this way. Now, if I had a structural model, you might have the same part of the same building, but with 3 separate structural columns. And on the right, you see the same thing. There's a separate ontology and a separate set of instances loaded up into a database in much the same way. Now, what we want is interoperability between those. And we know that those columns, A1 on that side and A1, L1, 2, 2, 3, 3, 4 on that side, are actually the same thing. So in Cloud BIM, we make this hypothesis. We state this hypothesis. Could we generate a new CBIM property graph or ontology and instances in which we're able to semantically enrich the model by relating the architectural column with the structural columns? And this means that the CBIM ontology is a whole new set of concepts which are the same thing, part of, connected to, and other relationships that allow us to then achieve multiple functions so that in future BIM systems, or design systems, we may be able to run all of those models in the same property graph cloud, but have different tools for editing each one, but have an agent, if you like, a CBIM agent, ensuring the consistency and integrity across those different models. So that, as a quick example, were I to have, were I to have a pipe in an MHP model, I might know that that pipe is attached to those columns. And in doing all of those changes, we may be able to provide that envelope that wraps up our new future BIM tools. And then, of course, in my final words, I will say this, that since our habit in our field is to provide 3-letter acronyms to all of these things, we might find one for this future thing. But all I've come up with so far is this acronym AICC-FPGCM. And of course, you're all welcome to propose something more concise and interesting. So what I've tried to say is that BIM model representation for AI applications is the key to my mind research challenge. Property graphs and linked data are one major opportunity, and that semantic enrichment, in order to do that and apply them, is the second area that really requires our attention. And so with that, I will thank you and hopefully have finished vaguely on time.